All right, so in this lesson, we're going to introduce what is the second big main idea of calculus. So over the past several weeks, we've been studying what is called differential calculus, which has to do with derivatives, which allow us to analyze rates of change. The second big branch of calculus is called integral calculus. And we're still dealing with the mathematics of change, but now we are studying total change. And just like before, we're going to worry more about what these things mean and how to interpret them first before we worry about how to calculate them. I'm going to start with a very simple example just to build some intuition behind this, and then we'll do the notation, and I'll show you how to do them in your calculator in this video as well. So make sure you've read this problem. I'm not going to read it out loud to you. It's an interval workout. So if you've ever done like an endurance sport like cross country, you're probably familiar with this. So you go hard and then you go easy and then you go hard again. And this is the graph of like what the intensity would look like down here. And notice what we're trying to figure out is the total distance traveled during the workout, and notice total change. So this is an integral. It's also very easy math that you already know how to do, especially if you've taken physics, but I think everybody's seen this before. It uses like that distance equals rate times time formula you probably learned in like middle school science or something. So to do this math, we're going to do just 0.25 times 24 miles per hour, 0.25 hours times 24 miles per hour, plus 0.1 times 17 miles per hour. And then notice we did 3 of these, and then we did 2 of these. So there's my math, and I'm just doing distance equals rate times time. And what we get, right, is 21.4 miles, right? And that makes sense because we were going 24 miles sometime and 17 miles for some of the other times. So this result makes sense in context. And this math is pretty intuitive math, right? So 3 times the time times the speed gives you a distance, right, for the 3 intervals. Now what's interesting and what's going to like motivate our new knowledge here is how this shows up on that graph. So this, by the way, is an actual graph of like from the workout software I use. But notice like I didn't give you axes, so let's say this is time and this is speed, right? Let's call it velocity. We know what velocity means now. So notice my time, my high intensity intervals, let's see, these are going to be 0.25 hours. Each time, right? And then my low intensity intervals in between, well, those are going to be 0.1 hours. And then my heights, well, my height is going to be 24 for each of these and 17 for each of these. Okay? Maybe you see where I'm going with this. If you study physics, you probably do. So this area of each of my little squares is the integral, is the total change. So remember, area for a rectangle, that's what we have here, is base times height. And for my orange rectangles, it's going to be 0.25 times 24, base times height. And then we have 3 of those, right? And then for my green rectangles, well, same thing, right? 0.1 times 17, 0.1 times 17. So and then we have 2 of those, right? So notice I do the same math here to find the area under the curve as I did to find the total change. It's the same thing. And that's the key takeaway here, is that the area under a graph can represent a total change, and that's an integral. Okay, we're going to do an example here of sort of a more calculus-y problem, but it really is the same thing. Before we do that, we have to introduce the notation. And the notation for this, I think it's a cool symbol. It is a curly S guy. And it gets bounds a to b of f of x dx. So you read that and read this out loud if you're in a place where you can, as the integral, that's the sign, of f of x, that's the function inside the integral, from a to b, that's your bounds. With respect to x, that's the dx. So the integral from a to b of f of x dx. And that would be, in this case, we're interpreting this right now as the total change or the area under the curve. Okay, so let's look at a familiar example of a squirrel running along a wire. So this is a velocity position problem. And do make sure you read it, but it's just a velocity graph. And the question is, how far does the squirrel travel between t equals 5 and t equals 10? So I'm going to go ahead and annotate that right away in my graph. And I'm going to write an integral for it. So this would be the integral from 5 to 10 of this graph is v of t, and that's from the text, dt. And then we want to do area. And area, I have trapezoids, or I can treat them as little rectangles. So let's do yellow piece first, and then we'll do the purple piece separate. So notice yellow is made up of a rectangle and a triangle. So we're going to use two different area formulas here. So the rectangle is just base times height, and notice my base is from 5 to 7 is 2, and then my height is 20. Plus my triangle is going to be 1/2 times base times height. My height is still 20. My base now is from 7 to 9, which again is 2 times 20. And that all together would be 40 plus 20 is 60. And then for my purple piece, well, it's again a triangle, and my purple piece is just going to be 1/2 times, it has a height of 10 going down, that's that negative 10, and a base of 1, because it just goes from 9 to 10. Okay, so I'm just applying area formulas that you guys know to the graph, right? And I'm getting the values off the graph. Now here's the catch, right? So notice purple is below the x-axis. So purple is a negative value. So I'm going to say my area is a negative 5. Okay? So my integral is going to be just the sum of those. 60 plus negative 5 is 55. So that is how far the squirrel has traveled. And here's our units. So we had meters per minute. Well, we integrated now. So we're going from velocity to a position. My units are meters now. Okay, so it's kind of the opposite of a derivative. Now, here's a more interesting question. If the squirrel is at 12 meters at t equals 5, what's its position at t equals 10? Well, that would just be its position at 5 plus the total change from 5 to 10, right? So it would be 67 meters, because we already know that my integral is 55 meters. Right, this would be a great time to pause and make sure you have all this. So this is a lot, right? So it's the notation, and then we're using the area under the curve to solve the actual problem right now. So the notation is really the only thing that is new, because you guys have done area problems before. We're also going to show you now how to do this on your calculator. So take these operations just like we know derivatives. This is going to be quick because you guys already know how to navigate this menu on your calculator. The button now, instead of Math 8, is Math 9. And we have now this familiar function e. We've done this Six Flags problem before. Now the question is asking us for an integral though. So I've typed it into my grapher. And now I'm going to do Math 9. Notice I get an integral sign. Fn int is the function. And we are going from 0 and then to 8. So I fill in my bounds, and then e is my y1, and then my d is dx. Okay? And there is my value. Make sure your calculator spits out the same thing. Okay, so here's my result. Notice I rewrote my notation. That's good rewrite to get practice writing it. And then it asks us, there's that word interpret that we're familiar with. So interpret my result in context. Well, remember this is the total change in the function, right? So this is the rate at which people enter the park is e. So e, the integral of e is what we get when we add those all up. So we would say this is the total number of people that entered the park from t equals 0 to t equals 7 hours. And notice I have, again, a noun, a unit, and a time. And notice my time has two values now. And then notice for part B, just like our squirrel problem, we can take a starting value and we can add it in to get a total. So that would be something like this, right? And we get 1870 and some change. Okay, so that was a lot. This is absolutely a video worth going back and re-watching if you feel like you missed something. So double check your understanding before you go.